We've done our project on anomaly detection and IoT networks. So first off, what is IoT? IoT stands for Internet of Things, and it's referring to everyday objects that connect to the internet in order to be communicated with by other devices that are on that network, such as a light bulb or a thermostat that you can control through your smartphone, tablet, or computer. The importance of anomaly detection in IoT environments has grown rapidly as the IoT industry has grown. Because of all of the competition within this industry, a lot of companies are doing whatever they can to release their product before others do. And as a result, security is something that's not always a top priority. And because of this, unprotected IoT devices are a growing concern because there's more of them out there as the industry grows. And the low hardware specs of these devices make security a little more difficult in the sense that you can't just put an anti-malware or an antivirus software directly on these devices. So in our project, we utilize machine learning to identify anomalous traffic in IoT environments. We did this utilizing a pre-existing dataset called the BOT IoT dataset, which is free and publicly available for academic research. And then below you can see a citation for this dataset. This is a diagram of the environment that was used to generate and record traffic to simulate an environment containing multiple IoT devices. So up here, you can see an ESXi cluster, which was hosting all of these VMs that you can see down here. These four up at the top are all Kali machines that were used to carry out attacks on these victim machines down here in the green. The Kali machines were carrying out attacks such as denial of service, distributed denial of service, OS and port scans, as well as data exfiltration and keylogging. This VM right here, the Ubuntu server VM, was carrying out multiple types of services that would be run in any production environment, such as DNS, email, FTP, HTTP, and SSH. And it was also running a service called Node-RED, which simulates IoT sensors. So it's kind of a way to have simulated IoT devices on a network without having that physical device there. So it was running a weather station, which was monitoring things such as temperature, air pressure, and humidity, as well as a temperature adjusting smart fridge, motion activated lights, a garage door, and a thermostat. Then also on this network, there was a tool called Ostinato that was running, which was used to generate very large amounts of realistic network traffic. So that way there would be more traffic to deal with rather than just the IoT device traffic and the Kali traffic. Then down here, this VM called Ubuntu Tap was used to collect PCAP files using T-Shark. As I just mentioned, the PCAP files were compiled using T-Shark, and then from there the data flow was extracted from the PCAPs using Argus. And then those flows were imported into a MySQL database for further processing, and after that additional processing was completed, it was extracted to CSV format, which was later used to train our machine learning model. Here we have a table featuring the different bits of information that were recorded from the packets. Some of them, such as attack, as you can see here, is not recorded by T-Shark, and that was something that was added in from the MySQL database in order to more easily differentiate the normal traffic from the attack traffic. Then here you can see the dataset that we use. If we go into it, so go into the PCAPs, you can see all of the different attack traffic was separated out, and then they were further broken down. So theft, there's keylogging and data exfiltration. Then from the scan, you have the operating system as well as service scans. And both DOS and DDoS are broken down into the protocol that was used. So it's HTTP, TCP, as well as UDP. Then if we go into here, we can see all of the different CSV files And here is 5% of the entire dataset. This was used to train the machine learning models, as the full dataset contains more than 72 million different packets, and having 5% is just a lot easier to work with. Then if you go in here, we have the final dataset, as well as the testing and training dataset, which were used to train our machine learning model.
Let us get to the project implementation details. We downloaded the bot IoT dataset provided by University of New South Wales and leveraged the training, testing, and input dataset for our project. The training dataset consists of 17 features and the actual result that are used to train the machine learning model. The training dataset is labeled with both attack and normal traffic. For example, 0 indicates normal packet and 1 indicates suspicious packet. The testing dataset consists of 17 features and the actual result as well. The testing dataset is used to validate the machine learning model. It is also labeled with both attack and normal traffic. The input dataset is used as input for the anomaly detection machine learning program to categorize the normal and malicious attack traffic. Here's a list of the features that are used for the anomaly detection program. All of these are input features, and attack 0 or 1, right? So this attribute is the actual classification attribute. So first we start by importing the required Python uh, packages and libraries. The NumPy library is used for numeric and scientific computation. Pandas library provides the data frame creation and data processing capabilities. Matplotlib and Seaborn libraries are used for chart and visualization. The first step is to load the IoT bot training data into the pandas data frame, and then we set sequence ID as the index of that particular data frame, and we proceed to load the testing data set and also set the index for the testing data set. So here is the output of the IoT botnet training dataset and the testing dataset. We are plotting the training and testing dataset in the chart to visualize the type of attacks that are contained in the dataset. So before feeding the data to the model, we would need to transform the features of type string to numeric values. The function convert to numeric classes performs the transformation task. So both the training as well as testing data sets are pre-processed through the function convert to numeric classes. Then we go ahead and remove the y values from the training data set, and then we are creating a correlation matrix, and then we're trying to plot the heat map using Seaborn. So here is the correlation matrix for the training data set. And we are performing similar steps on the testing data set as well. So here we have the correlation matrix for the features contained within the testing dataset. So the idea is to ensure that the features that we are considering are not strongly correlated. And based on our analysis of the bot IoT dataset characteristics, we are leveraging the classification machine learning algorithm. We used the the this particular cheat sheet provided by Skykit Learn. In our case, we have more than 50 samples. We are predicting a category, whether the packet is normal or anomalous packet, and we do have label data which we can use for training. There are more than 100K samples that we have in our data set, and hence we are using stochastic gradient descent classifier for our program. So having once we have here, we are creating an instance of stochastic gradient descent classifier, and we are training the classifier with the training data. The classifier is trained, and then we are printing the various coefficients as well as intercepts here. Then we proceed to test the accuracy of the model by comparing the original dataset with dataset target y with the predicted value of y. You would see, as you can see, our model prediction accuracy is 19.99% on the training dataset. We repeated the same task on the test dataset. We're able to predict that. We are able to see that the our model's prediction accuracy is 19.98%. The final step is to load the input dataset and perform the machine learning classification using the input dataset that consists of the input features only. And we are printing the input data as well as the various features as well as the data types. Overall, our machine learning classification program analyzed 3.66 million packets, and we identified 58 malicious packets contained within the dataset.